The effect of imperfect labelling on an LSTM deep learning intent classifier for assistive technology, by Joseph Russell and Jeroen Bergmann. Both authors were affiliated at the time of publication with the Natural Interaction Lab, Institute of Biomedical Engineering, University of Oxford. Published on the 25th of March 2025 in O. Palinko et al. Social Robotics, ICSR plus AI 2024. Lecture Notes in Computer Science, Volume 15561. Springer, Singapore. Recorded on audio with permission from the Springer Nature editorial team. The Springer Nature version remains the official version of record. Abstract. Intent sensing, the estimation of what it is that a human wants to make happen, is a useful input for collaborative robots, allowing them to intuitively detect and anticipate user needs. It is easier to detect an action after it has completed than it is to predict an action in advance. Therefore, it is proposed that a pre-trained after-the-fact classifier could be used to label unsupervised training data for a predictive classifier, and thus allow a self-learning system with a constantly expanding dataset tailored to the specific user. However, the after-the-fact classifier will not be 100% accurate, so this labeling will be imperfect. To determine whether such a system could be viable, it is important to investigate the effect of imperfect labeling on a deep learning intent sensing system. This is tested on time series data from an existing dataset of Parkinson's disease patients and controls, classified with a long short-term memory recurrent neural network to estimate intent over time. The results show that while large numbers of label errors cause a negative impact on the classifier accuracy, the classifier is robust to small amounts of label noise, with a label error proportion of 1/12 having only a very small impact, approximately 0.6%, on the accuracy of the classifier. This supports the viability of a self-learning intent sensing system. 1. Introduction. 1.1. Motivation. Assistive technology, such as human collaborative robots designed to help people of limited mobility, would benefit from intent sensing as a control input. Intent is broadly defined as what it is that a user wants to make happen. It may be broken down into 3 phases: recognition of activity transitions, inference of task goal, and predicting future actions. A holistic intent sensing system should incorporate all 3 of these aspects, predicting future actions before they have begun, and then updating this prediction as the activity commences, and continuing to refine it as the action takes place. In order to classify intents accurately, machine learning methods are appropriate, provided training data is available. However, it is more difficult to predict future actions that have not yet begun than it is to identify actions that have already taken place. In fact, a previous study has shown that the accuracy of intent prediction increases approximately monotonically as time passes, from before the activity starts, through the transition, and into the activity itself. This presents an opportunity. One method of improving the accuracy of the prediction of future activities is to acquire more training data. However, the amount of available training data is often limited. A method for acquiring more training data in real time, without supervision, would allow the predictive intent system to improve in accuracy over time, and to gradually become more tailored to the user. This study presents the proposal that a system can continue to collect data during use, and that the more accurate estimation of intent after an activity has completed can be used to label this data, which can then be added to the dataset used to train the predictive classifier, estimating intent before activity has begun. Retraining the predictive classifier with this ever-expanding dataset will allow it to increase in accuracy. However, the labeling is imperfect, as some of the labels used to train the predictive classifier with this will be incorrect. It is therefore desirable to investigate the effect of imperfect labeling on a classifier trained to estimate intent. If it can be shown that an intent classifier can still be trained to a similar level of accuracy with imperfect labeling as it could have been with perfect labeling, then this would support the proposed method of a self-improving intent sensing system as viable. 1.2. Background. The effect of imperfect labeling has been investigated for simple classification algorithms. This was tested for the support vector machine, SVM, k-nearest neighbors, KNN, and linear discriminant analysis, LDA, classification methods. And it was found that the SVM and KNN methods were robust to imperfect labeling, converging as data is added to an optimal solution comparable with that from uncorrupted labeling. The LDA classification method, on the other hand, showed more inconsistent performance, suggesting that robustness to imperfect labelling may not be a property of all learned classifiers. In the application of deep learning, other studies have explored the effect of imperfect labelling in general and specific contexts, particularly in biomedical image analysis. One such study investigated weak and noisy labelling, establishing a negative effect and suggesting methods to mitigate the impact such as label cleaning and data reweighting. However, these methods typically depend on foreknowledge of the statistical characteristics of the labelling. Such statistical information is unlikely to be available in the case of a dynamic intent sensing system, which will vary dramatically depending on the available sensors, the intents being selected between, and the conditions under which the participant is acting. 2. Methods. 2.1. Dataset. This study uses an existing dataset collected from patients with Parkinson's disease and non-disabled controls. 34 volunteers took part. 15 had Parkinson's disease, and 19 did not. Their ages ranged from 40 to 85, with 21 male and 13 female. Each participant wore 5 XSENS 9-axis inertial measurement units, IMUs, each providing accelerometer, gyroscope, and magnetometer data representing the participant's motion and orientation. However, this study only uses data from the single IMU on their right wrist. Each participant performed 3 activities of daily living, ADLs, under controlled conditions: unlocking and opening a door, buttoning and unbuttoning a cardigan, and making toast. Each activity was repeated 3 times consecutively. Data recording commenced when the participant was told to begin the task, and ended when the task was complete. The shortest task lasted for a little over 30 seconds. 2.2. Intent algorithm. The algorithm used to classify intent was based on the methodology described in reference 2. The single wrist-mounted IMU provided time series X, Y, and Z values for acceleration, angular velocity, and magnetometer data, along with a rotation matrix describing its orientation, totaling 18 features. The orientation data was normalized relative to the initial position, such that the initial position could not be used as a classification feature. The data was divided into time windows of length 500 milliseconds, with a 250 milliseconds overlap. The data from each time window was taken as an individual training sample to train a long short-term memory LSTM recurrent neural network. This was trained over 30 epochs, selected experimentally to minimize overfitting and training time, with 15 hidden units, a learn rate of 0.001, and a mini batch size of 512. Leave one out cross-validation was used, and as such, 33 of the participants were used to train the classifier, and 1 was withheld as the training set, the withheld participant changing 34 times with the mean accuracy taken. For the testing participant, each time window was individually classified. Then, for each time step, a majority voting system was used to combine the predictions from all time windows prior to that time step, producing an overall intent prediction for the activity updating with each time step. The first 30 seconds of each activity in the testing set were classified, less than the length of the shortest task, ensuring that all 3 tasks were valid possibilities to classify between at all tested time steps. The experiment was repeated 40 times and the mean accuracy was recorded, along with the central 95% confidence intervals. 2.3. Imperfect labelling. To simulate the desired imperfect labelling effect, a proportion of the training data labels were then changed to a different, randomly selected class to make them incorrect. A proportion p were changed, with p varying in increments of 1/12 from p equals 0 to p equals 7/12, and training repeated for each value of p. Increments of 1/12 were selected, as this allowed testing of 2 values of particular interest, p equals 1/3 and p equals 1/2. These are the values at which the proportion of incorrect labels becomes equal to the proportion of data from each class, as there are 3 classes, and becomes equal to the number of correct labels, respectively. Perfectly accurate labels were always used in the test set. It was hypothesized that for p less than 1/2, the accuracy would increase over time, as the classifier would train on more correct labels than incorrect labels, allowing it to still perform classification to some extent. For p greater than 1/2, the opposite would be true. More data labels would be wrong than correct, so the trained classifier would be wrong more often than it was correct. In this case, accuracy was expected to decrease over time. For p equals 1/2, there would be equal numbers of correct and incorrect training labels. The accuracy was therefore expected to tend towards 50%. 3. Results. Results from the classification experiment with different values of p, the proportion of training samples incorrectly labelled, are shown in Figure 1. Figure 1. Mean accuracy versus time after inception of idea to act for varying values of p, the proportion of training labels that are incorrect. For p greater than a half, accuracy tended to increase with time. For p less than a half, accuracy decreased with time. And for p equals a half, accuracy tended towards 50%. The top two highest accuracy values of p equals 0 and p equals 1/12, are shown in Figure 2, with the mean and central 95% of accuracies plotted. The two regions overlap considerably at all time steps, suggesting there is only a small difference between them. Over time, the mean accuracy of p equals 1/12 was 0.6% less than the mean accuracy of p equals 0. Figure 2. Accuracy versus time after inception of idea to act for varying values of p, the proportion of training labels that are incorrect, shown for p equals 0 and p equals 1/12, with the central 95% of results plotted, dotted lines. 4. Discussion. Figure 1 shows that, as expected, increasing values of p, the proportion of labels that are incorrect, reduce the mean accuracy of the trained classifier when tested on perfectly labeled data. However, the difference in mean accuracies between p equals 0 and p equals 1/12 was very small, approximately 0.6%, as shown in Figure 2, and at all time steps the central 95% regions of both lines overlapped considerably. This suggests there is very little difference between the classification accuracy when p is small. In a previous study, the after-the-fact accuracy of intent classification reached 99.99%, and would therefore be able to provide labelling of far higher accuracy than p equals 1/12, which corresponds to approximately 91.7%. This therefore supports the idea that the proposed unsupervised self-learning method of predictive intent sensing will be viable. The data in Figure 1 supports all three hypotheses proposed in Section 2.3. Fundamentally, the minimum requirement for the system appears to be that the probability of incorrect labelling must be less than p equals a half. If this condition is satisfied, then the algorithm will still be able to correctly classify user intent to some extent, with accuracy increasing over time, and so the LSTM classifier is robust to imperfect labelling, though to a lesser degree than the SVM and KNN methods as tested in Reference 4. Collecting more training data would be expected to reduce the impact of the imperfect labelling. This will be investigated in a future study, which could apply the algorithm with generic and publicly available datasets. In a practical system, the accuracy of intent prediction can also be improved by adding more sensors with different sensing modalities. Future work could explore these effects for a wider range of classifiers, and include an analysis of the different types of label noise and their impacts. Now that it has been shown that imperfect labelling might have limited effect on the accuracy of LSTM intent classifiers, further work should implement the proposed self-learning system, using an after-the-fact activity classifier to provide imperfect labelling to continuously train a predictive intent classifier to anticipate user needs before activity begins. Funding. This research was funded by the Biotechnology and Biological Sciences Research Council, BBSRC. Grant number UKRI 012.